Good afternoon, everyone. We're just about to start. A few latecomers coming in. This is the FT8 lecture. If you're not interested in FT8, you're in the wrong room. Just please take a minute to note the exits, the fire exits at the doors here. In the unlikely event of an evacuation, the assembly area is the Nightingale car park. It's my great pleasure to introduce Neil Smith, G4DBN. And I'm told this is what the lecture is about. He's going to tell you what really matters when you're looking for the ultimate performance with FT8 and other digital modes. He'll demonstrate the most common problems and how to resolve them. And he will use real-world examples of practical pitfalls and present tools and techniques to help you improve your digimode performance. And if you don't get any of this the first time, this session is being repeated tomorrow morning at 9:15. So it's all yours, Neil.
Thanks very much, Richard. That noise and picture is really something that you could almost put it into Tate Modern as a piece of modern art. The music could have been done by Boulez. It could have been done by Philip Glass. Fantastic noise. So, what started me off talking about FT8? Well, I'll go into that in a little bit more detail. I'm going to talk about the myths and the horrors. And there are certainly some horrors. Things to tweak on your transmitter. I'm going to talk about monitoring tools. I'm going to talk about how to optimize the hell out of your receiver. I'm going to talk a little bit about software. And I'll probably manage to get a little bit in about the future. So, what was the motivation for this talk? Back in the day, I was having a play with this fantastic new toy, FT8. And I was having wild fun. And as with most things, I shared it on Twitter. I always share things on Twitter. My entire life's on Twitter. And then suddenly, a Twitter troll got me. Turn your ALC down, he said. You're over-deviating. Interesting. Well, you know, I've set things up really well. It's got all the proper test gear, and I've really tried hard with it. I'm fairly... Okay, yeah, so, yeah, I'm splattering all fine, okay. But, you know, my rig doesn't even have ALC, so I can't turn it off. And my spectrum analyzer tray says, and this was the best thing, you're just embarrassing yourself. So, Mr. Twitter Troll, this talk is entirely dedicated to you. So, what we are going to talk about, not going to talk about, is Marmite t-shirts. We are not going to talk about mode wars. And we're not going to talk about the end of ham radio as we know it. And one thing I will promise is I'm not going to mention maths, algorithms, or equations. I may possibly mention the odd mathematician, but I'll give you a warning. And I'm certainly not going to tell you anything that you can read in the manual. So don't expect this to be me reading out a manual. It's about my personal FT8 voyage of discovery. I am a hacker and an engineer and a person who messes with things and makes things. I take clocks to pieces. And, well, I did when I was 6. So, a few myths and legends. Let's just check. Reality check. It's mind-bogglingly popular. Yes, we know that. It uses 8 tones spaced 6 and a bit hertz apart. Yep, fine. And the symbol rate's also 6.25 hertz. That's pretty convenient. It's a weak signal mode. What's that mean? Has anybody got a weak signal? Well, I always try and be nice and loud. Oh, very close there. We nearly talked about maths. It does something complicated with Costas arrays and all sorts of other clever stuff, which you can read about on the internet. There are papers about this. It's great. Now, one of the things FT8 has said is it's a single tone, constant envelope mode with 50 hertz bandwidth. I like claims like that because they're measurable. So, if we're going to get the best out of this mode, we'd better find out how it really does work in practice. So, first question, is it really single tone constant envelope? Well, that's my radio starting off with a nice bit of transmission there. The tone is probably about 2 kilohertz, and it looks like, yeah, it's pretty much constant envelope, and there's only a single tone there, perhaps. But remember when you got CW clicks? Well, isn't that going to be exactly the same thing as a CW click? That is effectively a wideband splat. You've just gone full power instantly in a millisecond. If you actually look at the spectrum that you're going to produce from something like that, so there's a little sample. If you do some Fourier analysis, sorry, maths, you end up showing a spectrum which is really quite wide, and it's actually something like 4 kilohertz wide at the 20 dB down point, just from that initial turn-on splat. Now, when you actually look at what these look like, whoops, sorry, go backwards one. Dear. Come on, machine, catch up. Right, we'll get there eventually. So there we have the this startup splat, and you can see that is tailing out all the way over here. It's over 2 kilohertz wide every time your FT8 starts transmitting. So it looks bad, but does it sound bad? It's like 20,000 leagues under the sea, isn't it? It's not that serious when you listen to it, but if you've got 200 other people transmitting at the same time, potentially it's a problem. The splat only lasts milliseconds. Now here's the killer. If everyone's got a precise clock, all those splats happen at the same time, and therefore we don't really care about it much. There's nothing you can do to fix it other than getting Joe to rewrite the code and changing all of the way the thing works. It's all Fourier's fault. You see, mathematicians, do we care? Well, it annoys everybody else on the band, potentially, and it means that we all need precise timing. So, how are we going to get precise timing? Well, we've all got the internet, most of us anyway. So if you've got the internet, use NTP. NTP, great little thing. Download Mindberg, marvellous little product. Not going to tell you how to install it, but it'll be on the website afterwards, so you can download it if you're not using that. If you prefer Dimension 4, great little product. Those will mean that your time on your computer is going to be within a few milliseconds. Or you could do it that way. Smartphone, as long as you're within half a second, it's probably good enough. Anybody still using Windows time? Please don't. So, we've looked at the start of the FT8 and found out there's a splat there. Do they actually change? Is there any problem when it changes tone? FT8, the beauty of it is that it changes very smoothly at the crossover there. As everybody can see, that is something like 230 hertz, and that is 200 hertz. And it looks pretty smooth. But actually, if you zoom in on that, that's a pretty sharp kink. And sharp kinks are not good things when it comes to transients. So, effectively what's happened is you've put a square wave FM modulation in there with no filtering. So, bound to produce a bit of a mess. Well, looking at that, that's not too bad. It's not obvious that there's any sort of discontinuity. However, once again, if we actually look at what the spectrum is like, we end up with that. And it's a bit of a splat. It's nowhere near as bad as the startup splat, but you're still going to be 400 hertz wide each time the tone changes. So we need to take that into account. The other thing is that all this energy that you're putting out into those sidebands may go outside your transmit filters. Now, if you start slicing bits of this off, you're going to affect the main tones. When the decoding happens, there's going to be some smearing. So, you know, you really need to be transmitting the whole of that if you can. Sounds like that might not be very neighbourly. That's what each of the individual tones looks like. As you can see, there's a 400 hertz wide splat each time the tone changes. And you can probably see that where there's not much of a tone change, there's not much of a splat, as you'd expect. So 400 hertz wide, 25 dB down, that can be pretty loud. But again, if everybody's got their timing right, it's all happened at the same millisecond. The trouble is you haven't got many milliseconds in a 6.25 board system. So let's have a listen to see if that really matters. This is slowed down half speed. Well, I can't hear any clicks. I don't know about anybody else, but if we have a look on there, there are some definite little clicks coming out there. There's definite sidebands. You can almost see there's some feathery bits here. but humans don't hear it. Computers maybe do. At the end of the transmission, when that transmission stops, suddenly all that energy goes away and it turns off. In a CW transmission, you would try and tail it off to stop it from causing a key click from the off. Unfortunately, the way this seems to work, with a nice low frequency tone there, it looked like he was trying to do it damped and fading it out, but that's what happens at 1500 hertz, and it just literally turned off and went back to zero. So that's a really, really loud splat, and if you have a look on the spectrum of most FT8, the turn-off splat is actually worse than the startup splat. So, is it constant envelope? Well, it depends. Rather a little picture, but there you can see this is the average. The blue line is the average, and that's what my transmit filter's done for a 15-second transmission. It's sliced off some of that top and quite a lot of the bottom. So it does matter a certain amount. There will be a certain amount of AM. I'm blaming Hilbert for this one, mathematicians. So, any step change in frequency results in sidebands and carrier amplitude modulation. But at least it's linear phase. But is it linear? Well, there's steps in it, so you have to redefine what linear means. Okay, so next thing, is it 50 hertz wide? Well, not quite right, unfortunately. That is what a 15-second spectrum looks like. You'll see there, round about minus 20 dB, it's about 70 hertz wide, not too bad. However, by the time you get to minus 70 dBc, it's a kilohertz wide on average. So, you need to make sure that you're bearing in mind that FT8 is not 50 hertz wide. You've got to transmit the whole of it. Only that bit really matters, but if you chop off the rest of it, it starts to cause problems with inter-symbol interference and all sorts of stuff. So only the loud bit really matters in theory, but we shall see. Anyway, so is it multitone? Is it variable amplitude? Well, yeah, a little bit. We need to care, but because it's nice and easy to deal with signals like that, we've been doing this for years. Most of our SSB radios can transmit quite linearly, so all that FT8 stuff goes through the SSB radio pretty well and goes out there into the outside world. Oh dear, what's that? So you've plugged in your sound card and you've got everything working at 650 hertz. There you are, you're on transmit. Power looks great, and the neighbours start to complain. And you've got over here a very nice copy of your tones, but they're 150 hertz wide. And the reason is you've overloaded your audio, so you end up with your nice, beautiful sine waves suddenly ending up as rather square waves with good odd harmonics. Here's a couple more. So that's actually a second harmonic. That one there was a nice example where he'd managed to get his second harmonic and his third harmonic. So that was going well. This one, sorry, that was the third and the fifth harmonic. This one here, he's got his second harmonic, his third harmonic, and there's a bit of his fourth harmonic there. So harmonics are very popular with FT8 users. If anybody can tell me how on earth they did this, I have no idea. That was recorded off the air. That is the 10th harmonic, upside down, back to front, overlapped. Brilliant. Just, yeah. So, next problem on transmit. A lot of people using linear power supplies, and there's hum and ripple. There is a bit of hum coming out there. That causes amplitude modulation, and so you're getting some harmonics. The FT8 trace there, which I'm not going to let on who it was, but he's got the fundamental, he's got plus or minus 100, plus or minus 200, and actually somewhere in there, he's even got a little bit of plus or minus 300, and all of that decoded, so he came in 7 places. So just watch that ripple. This one was even more interesting. I don't know how he did quite manage to do this, but this was on 10 meters, and I thought, oh, the band looks remarkably busy. Tom, M0LTV, actually sent me this. Tom pointed out that actually they're all the same call signs, and actually those are all hum products, every single one of them, and it goes out as far, I think that one decoded, that one decoded. Later on, I think Tom actually managed to get a sniff of that one, so extraordinary, very impressive. We couldn't work out how he managed to notch out the one at 840 hertz. That was obviously something very clever. The other thing you've got to watch is hum can actually be at 10 kilohertz from your switch mode power supply or whatever. I was caught out by that on 3 centimeters. I was transmitting away and somebody said, you're also 15 kilohertz up and 15 kilohertz down and 30 kilohertz up. So found out that my switch mode power supply had gone a bit wonky. So what matters on transmit? Levels, control of harmonics and hum and ripple, and probably keeping tones clear of the filter skirts. That's not so important as everything else. The main thing we ought to do is we ought to be a good neighbour by avoiding overdriving things, clicks, hum, and so on. However, even if your signal is absolutely rotten, you can still work the DX, so you probably don't know anything's wrong. Does ALC pumping matter? Well, actually, in the experiments I did, not a lot. If the power supply droops because it's not got big enough storage capacitors, it doesn't matter. A bit of drift, round about, say around about 2 hertz per second, it doesn't really matter, it'll still decode. And weirdly, if you slam it through a speech processor, you would think that would cause all sorts of problems. I could not see any detectable change on my ancient TS440 or my new SDR. Absolutely no impact from speech processing, which is a bit counterintuitive. Levels matter, hum matters, harmonics matter. Some of the other stuff probably doesn't. So we've got to concentrate on knowing what the levels are throughout the entire transmit chain. It's important that we keep the levels high so we don't get any hum pickup, much the same as with any audio design. We need to be linear where it actually matters. We need to control hum loops and power supply ripple, but probably the thing that most of those people weren't doing is they weren't working split. Now I'm hoping everybody here is working split, but if not, we're going to find out how to do it. The other thing is that they've obviously not got any monitoring. They're not monitoring their signals because they're so dirty. If you can't monitor it, how are you going to fix it as well? So, one of my pet hates, ALC. Do not use ALC. If you've got ALC that you can turn off, turn the damn thing off. Actually, doesn't really affect your transmit signal, but my God, it annoys the neighbours. Yeah, I did mention ALC. Please turn it off. So, linearity, I would say use maximum level on all the sound devices within your computer. So anything that is actually a sound device in the computer, set it to within maybe 4 or 5 dB of maximum. You don't want anywhere where any noise can get in later on. Set the mic gain on your rig so that you're attenuating at the mic socket. So you've got a nice big fat signal going in, attenuate at the mic socket if you really must use the mic socket. And then set the mic gain to see if you can get full power on FTA. And then, with the slider on WSJTX, which is the little power adjuster, drop that by 6 dB. Now, of course, what should happen is that your power drops by 6 dB. If it doesn't, you're using too much power. So wind it back until you've got the thing linear. It's a pretty nice, easy test. You don't need any test gear to do it. Just literally go onto the slider, slide it down by 6 dB, measure your output power, and you need to be certain that you're not actually in compression. Now, the best way of testing it is the same as it is with sideband. Do a 2-tone test. Oh, that sounds hard. You used to have all these complicated oscillators and very fancy kit. Well, these days, I just generated 2 nice pure tones in Audacity, made a new track and exported it. The instructions will be on the website, so it sounded like that. That's actually my 4-meter setup with a quick test, and it's ugly. But basically, if you turn back the gain until your INDs are acceptable to about the minus 40 dB or better, then you're probably going to be okay treating that as your maximum power level to use on FT8. Whatever happens, you ain't going to be making your signal any worse than it already was. Record the settings for every band. So, how do we work with cat split? Well, the point about cat split is that it stops most rigs from producing harmonics by adjusting the transmit frequency. So if you're operating on a frequency, on a tone of a couple of hundred hertz, it's not the best place to be operating. The rig likes to have a 1500 to 2000 hertz tone, so that the harmonics are way outside the passband. So nice easy way. Here we've got our radio on 14074. We've got the receive tone set to 800 hertz, and the actual receive frequency is 14074.8. The FT8 program, whichever one you're using, sets the transmit to 14073 and sends an 1800 hertz tone. Result being the transmit signal goes out on 14074.8. Perfect. So that should fix all those cases of harmonics that we've seen so far. This is not an excuse to be sloppy about levels. To enable it, literally all you've got to do is tick one of these, is put a blob in one of these boxes. Almost all rigs work with fake it. Fake it sends a command on each transmit cycle to say, please change frequency to this frequency. So if your radio is a bit slow about its cat frequency changes, then the other alternative is to use the rig option. What that does, it actually runs your rig in split. Debugging that was an interesting way of spending nearly a day and a half. So don't go there. Fake it really does work. So some older rigs particularly might be better with the rig setting. Very quick note, if you want to debug Cat, people say, I can't see what's going on, this USB serial, and I can't see inside it. There are tools. Wireshark's a great one. This one here was from my FDM Duo, and we've got there some of the signal coming in on the USB. That's what it looked like. The actual text said, I am operating on 14074 in USB mode. So really easy, useful little tool, very simple. Just download it and you're off. And Hamlib has a little function called rig control, which lets you test out cat stuff. So if you've got weird cat problems, you can always run rigctl, and it will send the Hamlib command that the program would send. So WSJT says to Hamlib, please send an F command to set the frequency. And you can do that manually using rigctl. Nice, easy thing to do. You just send it the F command. Again, don't bother reading all this now. I'll put this up on the website. If on the F command there, it said we're operating on 14074 again, and when we did the M command, it said we're running on USB at 2400 hertz. So nice little tool. So how are we going to reduce the hum and noise on our analog input? So use an audio transformer. Everybody's used audio transformers for this for centuries. It's old technology, it works brilliantly. I always put a pi or a T pad either side, simply to make sure the impedance match is good. This little setup that I had here, I tested it, and it was flat from 150 hertz to over 40 kilohertz, and the phase shift was minimal at 3 kilohertz. So nice, easy little circuit. Throw it together with a bit of Veriboard there. I haven't used Veriboard for centuries. That's actually 0.156 Veriboard as well. If you've got a serial connection and you're getting hum and noise problems being picked up from that, there's lots of these little OpIsolators. I'd never really played with these until 4 weeks ago, and I stuck one of these in and tried it just with a simple resistor going into the LED and another resistor as a pull-up on the photo transistor. But I couldn't get it going above 38,400 baud. Luckily, my old radio that I was using it with only operated at 4,800. But if your rig goes much faster than that, you might have tricks. But that got rid of all of the noise that was left. So when I disconnected the wire, I couldn't hear whether the rig was connected or not anymore. So nice, easy trick. So not only does it help a bit on transmit, but it also reduces noise on receive. Power supply ripple. I'm not even going to tell you how to stop power supply ripple. Just fix it, please, guys. Hot switching, right. FT8, when it sends the PTT low, on my setup, it takes 710 milliseconds before the first tone starts. So PTT goes low, everybody twiddles their thumbs, and then the transmission starts. If you have got hot switching going on, after 710 milliseconds, you need to have a very close look at your life and decide what you're doing wrong, because there's enough time there, even for my big 3 centimeter waveguide relay to flip over. So, you know, it shouldn't be a problem. So, we've got a beautiful clean transmission, and my analyzer's showing it very beautifully there. Yes, that looks absolutely spot on. However, not everybody happens to have a rack full of analyzers in their living room. So, what can we do to prove our signal stream? Well, we can phone a friend. Not always the most convenient. If you haven't got any friends, you could try WebSDR. The WebSDR, if you're loud enough, you might be able to see your harmonics. You can't zoom in very well, so it's an option. But again, you've got to have a signal path to that. So we're a bunch of techies. This is 2018. Let's see if we can use some technology instead. I don't want to scare anybody with SDR, so we're going to talk about this as radios. So there are 4 steps to heaven. Nice bit of free software, a nice simple little receiver, which we're not going to call a dongle or SDR or anything like that. It's a receiver, and a little HF converter. Well, it was going to be a simple attenuator. I think that's all of the attenuators out of my box. So let's have a look for how we can do some way of monitoring our signal without having to use a whole pile of attenuators. So, whoops, go back one. So you can use a little loop like that, which I did, but obviously it's a bit unpredictable, and it's really hard, and you put it down to type something and the signal changes. So I made myself this little coupler box, which just happened to have a coupling of about -80 dB. So if you stick 100 watts through it, you get a nice, comfortable signal into the front of your receiver to have a look at the signal. I actually decided to make this, I think it was 7 days ago, and it took me 1 hour and 10 minutes, and about half of that was finding the box. Very, very simple little thing. I actually ran a program to find out. There we are, so that's a bit of a better close-up. It's just a slab line, like you would use for a VHF sampler, but obviously because we're using it on HF, it's effectively an 80 dB attenuator. So, I calculated the line widths using a little program called ATLC2. Don't know if anybody's ever used it, but it is brilliant. ATLC2, you draw a picture of a transmission line cross-section. So this is a slice sideways through your transmission line. The red bit's plus, the green bit's minus. You can put in all sorts of different materials and dielectrics, and it goes away and it does all sorts of very complicated maths. And 9 minutes later, it says 50.11 ohms, so that was a good guess. That took me about, I think, 3 iterations to get that right. So I used that to work out the size of the slab line, soldered it all together, tried it all out, and remarkably, 15 minutes later, after doing all this lot, it was working, and there I was listening to my signal. Quick aside for VHFers, above 125 megs, you don't need that HF converter because the native RTL SDR will work from 125 megs up. There is a tweak you can do with direct sampling Q branch. Just don't even go there. Just don't. Use the little converters. So now we've had a look at this, let's have a look at lovely, low-cost, simple monitoring setup. Okay, no, that's actually my living room. I take it everybody has got 342U racks full of test gear in their living room. Well, I have. So that's maybe on the expensive side. So this is a bit better. This is more, it's a laptop off eBay, and we've got our signals coming in into the coupler. Nice big fat dummy load. There's our RTL SDR receiver, and there's our converter. And it just sat there, and most of the things I've showed you so far came out of this. Nice simple little thing. So let's have a listen to what it sounded like. Sounds pretty much like an FT8 signal. And as you can see, it shows us the splats on startup quite nicely and the intertone splats. This is a bit closer in, and as a result, you can see the sidebands that it creates. So, you know, they're not just mathematical, they are real, and that's the overall shape of the signal. That is between, I think, 1400 and 2000 hertz. That's about 600 hertz wide. Nice little system. I had never used it before, what, 3 weeks ago? And if I can learn it, anybody can learn it, right? I tried the NULEC as well. It's actually brilliant. It's a really good little receiver, but it's thick end of 90 quid, so don't go there, unless you really want to play on it. So now, with no more excuses for any audio nasties on transmit. Levels are right, linearity's right, hum loops have been shifted, nobody's got Ripple, and we've got a way to do monitoring. So far, so good. Now let's have a look at receivers. So, effectively, we've already done 5 of the problems that we might have with receivers. So, what's left? AGC and levels, and software features, shall we say. WSJTX documentation says disable AGC, which is great if you can. And it says set the audio level to give about 30 dB on the gauge. Doesn't really explain why. I did some tests and I actually found out that going from the 30 dB level, you can go down to 0 and then go down at least another 20 dB and it will still decode perfectly well. Down to, I think, minus 96.5 dBm, I was still getting decodes, but 30 dB is a good compromise. People always say, well, would it help the program if I narrow my receive bandwidth? Would notch filters help? And would my noise blanker help? So when you've got AGC, usual problem, big fat AGC signal, it depresses everybody else so you can't hear them. So the weak signals nearby get flattened out. With AGC off, you would be absolutely deafened, but FT8 is not human ears, and it doesn't care. It's got a 50 dB dynamic range at least, so it really doesn't care if you turn your AGC off very much. If you can't turn it off, you're going to have to play a game balancing the RF and AF gain until the point where you don't see dark shadows like I was getting there. Set the AGC as fast as it'll go and the gain as low as it'll go. You'll probably end up losing some of the dynamic range as a result, but you haven't got very many choices. So save up for a radio with an AGC switch. So this 30 dB band noise level is just a starting point. Somehow I seem to feel that 40 dB works better for me on weak VHF, but I've got absolutely no scientific proof. However, the effect it has on my reception is brilliant. If I set it to 40 dB, I can always hear much better than I can at 30. If you've got a second radio or a friend, get them to send you a signal and make sure you can get solid decodes right down to 30 dB and right up to 80 dB. If you haven't got any friends, well, you can use a second radio. But make sure, unlike me, you write down the level and gain settings for each band because you will forget them. You should be able to get 50 dB. So this was mid-evening, 80 meters, and I sent myself a transmission, which is just a pure tone right down the middle there, and that was at something like just over 80 dB, and nothing really affected decoding at all. Hardly any obvious effect. As soon as I turned it up to 86 dB, that happened. What I did, this is with it at about 86 dB. So I thought, what happens if I drop a big fat notch down there and put a square notch over that section, and it managed to decode almost perfectly, despite the fact that this interfering signal would have been at plus 100, completely impossible to decode. The beauty of that is that this is one of the cases when you can help WSJTX and the other programs by removing something that takes it out of the limits of its controller. So what about noise blanker? Well, here's a few little SD8 things that I generated and recorded. Yep, so there's a bit of signal in there somewhere. that doesn't sound so good. And that's with blanked out bursts. Sounds pretty horrific, but here's the thing. Every one of those decoded perfectly with plus 16 dB. FT8 does not work like your ears, it does not care, but the time to use the noise blanker is when those pulses would take it out of the 80 dB range. If you're going above 80 dB with your clicks, stick your noise blanker on, it's not going to hurt. The fact that there are gaps in the transmission, FT8 really doesn't mind that much. You can take out an extraordinary amount of an FT8 transmission. You can get a solid decode on the first 6.7 seconds of the transmission. But yeah. So what about this timing thing? This DT column that started off really to do with working out the delay on moon bounce. If your clock's wrong, you'll probably have a DT value that's not 0. What I did, I stuck a loop in there and let it loop round a little bit too short, so it wasn't 15 seconds long. So gradually, it went from 2.5 seconds ahead to 2.5 seconds behind, and all of those decoded perfectly well. So you'll be all right anywhere within 2.5 seconds on FT8. However, don't. Just stick it on the right time. Somebody did actually say, oh yes, but if I stick my clock 100 milliseconds ahead, I am actually going to be the first to be decoded. Yeah, okay. Call first. When somebody puts call first on, what does that actually mean? So the other stations put call first on, he's sent out a CQ, and what happens on the decode? Well, first thing that happens is the list is, in general, in ascending frequency order. Stations that are on your little green bracket where you've said, this is where I want to receive, so 1840 hertz there. Anything on 1840 hertz goes right to the top. And then some things take a bit longer to decode, and they go at the bottom, but again, in ascending frequency order. So, what's the strategy? The strategy is, first of all, try their transmit frequency. If that doesn't work, try and find somebody that just worked. If that doesn't work, go down to the low end. Remember to tick hold transmit frequency. Otherwise, you're going to transmit in the wrong place. Right, what software should we use? Well, WSJTX, I tend to use it a bit. I actually like JTDX a lot now, and MSHV's catching up. There's lots of choices out there. Which one you should choose? Well, actually, I use all three at once. And I use virtual audio cable from Eugene. Brilliant little bit of code. Works very solid with me. There are other virtual audio cables. What this does is it listens to the output of my radio and then makes 3 separate sound streams that I can connect all these to. And that way I can run, I've actually had up to 5 different decoders running all at the same time when I'm doing JT65 stuff. So again, don't bother writing it down now, but that is a virtual audio cable is my favourite. There are others. You have to pay for Eugene's code, but it's not much. What about FT8 on VHF then? Well, here's some Doppler traces. I suppose G3YDY might recognise his trace on this side here. This is your signal, Paul. I don't know which frequency you were actually transmitting on, but you were very, very good decode on 2 different ones, and these decoded as well. As for that one, what frequency is that station on? You cannot see the fundamental. I was actually beaming south. That station was over in GI. So, yeah, really difficult to decode, and it's a major problem. Round about that sort of 300 to 500 kilometre range, where there's a lot of aircraft Doppler. So, am I saying that FTA is no good on VHF? If you can work D4, 4,300 kilometres away, I don't think there's any argument that FT8 works okay on VHF. Absolutely stunning. While you're at it, make sure you tick the box that says PSK reporter, reports to go through, because then everybody else sees what you're working, but even better, you can see who's hearing you. Marvellous little website. Just remember to call CQ. The details of doing all this lot on VHF and microwave is a completely different lecture. But if you've not tried 5-second period JT9S fast on 23 centimetre aircraft scatter, boy, you've never lived. It's,
You can hear more about that on Sunday.
good stuff. However, the sound of relays falling to pieces is supposedly quite serious. Fox and Hound modes, I'm not going to say much about. There's a bit of politics going on here. I don't know if you've noticed, but people who aren't exactly the expeditions are running as Fox and Hounds mode because it makes them feel great. However, there's a couple of things that you need to be aware of. The Fox can set a number of different things that they categorize the incoming signals, so they put them in sorted order. They may say limit it by signal strength. They may say limit it by distance. There's a few other things there. You can just do it at random or grids or whatever. Anybody ever thought that the way of doing this, if they tick it by distance, is just to put the wrong locator in? Yeah. Good luck with the QSL cards if you actually use that approach. So if you're trying to work one of these guys, maybe crank the power down. They're going to be transmitting multiple different signals, 60 hertz apart, and they will be working you on higher frequencies, but hopefully they'll be in the clear. The way this, again, it's a whole new talk to talk about Fox and Hounds mode. It's a very interesting development. What I don't know is how well this caller selection algorithm works, but you have got to be louder than everyone else on your frequency, but only just. So what about the forthcoming protocol changes? So the announcement came out. FT8's being redesigned because they made it too short to start with. 6-digit locators, extensions for contesting, and this fairly interesting transport mode. A few other little tweaks, but the ones I'm interested in is 6-digit locators. I wanted a bit more than that, but it's a bit of a waste of bandwidth. And then there's FT8 call. Yeah. There will be a period of managed overlap. Now, I don't know if any of you have ever done any big IT installations where you've got multiple tens of thousands of users, and it's really easy to get managed overlap. No problem whatsoever, it'll work fine. Sweden, 1967, changed from driving on the correct side of road to driving on the right side. So, you know, they managed it. What could possibly go wrong? So, recipe for success. Transmit a clean, stable signal. Be loud, but only just loud enough. Adjust your levels, understand your levels, and record them so that you know how to set them again. Monitor your transmissions, unlike the bad guys. And if you haven't ever played with these SDR thingies, have a go, because it was a doddle, and it's so much cheaper than a spectrum analyzer, and also you can put it in your pocket. And optimize the hell out of your receiving system. So, I promised you some FT8 secrets. What are they? Well, it's just good engineering and good operating like everything else in ham radio. Thanks for listening.
Thank you very much, Neil. We are a little bit over our time, but if anyone has a burning question.